Dr. Ranjani Parthasarathi is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is a series of lectures on computer architecture. So, we will take a quick review of the topics that we have covered so far. So, we have looked at what goes into a computer, what are the functional units, what are the basic operational concepts, and we have also looked at some performance measurement issues. So, again repeating the same big picture, this is our von Neumann model: processor, memory or storage, input output, and we have the interface between the input and the output to the processor. Repeating this so that this picture gets into your mind very nicely. The operations in a computer, remember that activity in a computer is governed by instructions, and to perform a task, an appropriate program consisting of a list of instructions is stored in the memory. Individual instructions are brought from the memory into the processor, which executes the specified operations. So, this is what happens inside a processor. Okay. Now, with respect to the data which is to be used as operands is also stored in the memory, and the instruction execution takes place in multiple steps, and we use a simple data path or a control path which will tell you how the instruction gets executed. So, we understand the whole instruction execution in terms of the data path and the control path. In terms of performance, there are three important equations that we have looked at. This we need to remember these three equations because this is what will tell us how well our process that is being designed is going to work. One is the clock cycles. Number of clock cycles is given as instruction count into cycles per instruction. CPU time is calculated as instruction count into the CPI into the clock cycle time, which is given as instruction count into CPI divided by clock rate. So, either I say into clock cycle time or I divide by clock rate. And the CPU time as a whole can also be written as the instruction count is nothing but instructions per program, CPI is clock cycles per instruction, and the clock cycle time is number of seconds per clock cycle. So, these three if you remember, you will be able to understand how you will have to measure the performance of a system. Okay. So, that is what we have looked at so far. Now, from today's class we will start looking at how the instructions are designed and how these because these instructions are formed what we call as the language of the computer. So, the language of the computer is something that we need to understand. So, how is it that we design this language and how is it that these instructions will be actually executed? That is what we will start looking at from today onwards. We start off first with understanding what we mean by an instruction set. So, what is this instruction set? Instruction set is the variety of instructions that you have for a computer, okay, or what we call as a repertoire of instructions of a computer. So, different computers can have different instruction sets, but mostly they have many aspects in common. Okay. So, in general we will look at some certain common aspects and then we can look at examples of different processes which have different instruction sets. Okay. Early computers had very simple instruction sets, okay, and they had very simplified implementation, but as the industry progressed and more and more interesting designs were produced, we found that we moved towards many complex instructions and computers which did much more than what these early simple processors did. Many modern computers today, they have complex instructions, but there are also many computers today which have simple instruction sets, which are called as reduced instruction set computers. We will just briefly take a look at what we mean by that. Okay. So, first of all, let us look at what are the operations that these instructions are expected to perform. So, which means we must identify what are the must perform operations. So, what is must perform operations? We know that you will have to transfer data between the memory and the processor registers, between the memory and the processor, right. You need to bring data from processor to memory or from memory to processor, this needs to be done. So, we need to have instructions which will be able to do this data transfer. Then we need to have instructions which will do the arithmetic and logic operations on the data. Okay. Plus we will need instructions which will do IO transfers, and we will also need instructions which will do the program sequencing and control. That is, what is the sequence in which the program has to be executed, and if you need to do some control of the sequencing, that also should be provided. So, that is, must have instructions which provide these capabilities. Okay. So, how do we look at these instructions? Okay. So, let us understand it in terms of some typical instructions under these various classes. So, these are terms that you would have probably heard of. So, let us look at these typical instructions that we have. So, typical instructions would be data transfer instruction, arithmetic instruction, logical instruction, control instructions and IO instructions. At least you can classify it into these 5 types. So, data transfer instructions would be a move instruction, a load instruction or a store instruction. A move could be a move from a register to another register. A load would typically be from a memory to a register, a store would be from a register to a memory and so on. So, these are data transfer instructions. Then we always have many arithmetic instructions. Examples of these are an add instruction, a subtract instruction, a multiply instruction, a divide instruction, a compare instruction and so on. Logical instructions and or XOR operation, a NOT operation, shift operation and so on. Many of these are bitwise kind of operations. Okay, these are performed on different bits. Then you have control instructions like jump. Okay, a jump would typically jump from one location to another and start executing your program from that location. A branch, a jump or a branch, these are terms that are used. And this jump and branch could also be done conditionally. So, you have instructions like jump if not equal or jump if equal, things like that. For input and output, normally we have operations of instructions which are called as in instruction and out instruction and so on. Coming to this RISC and CISC type of architectures that we just mentioned a little earlier, based on the instruction set that we have, we normally divide the architectures into 2 types, a RISC type of architecture and a CISC type of architecture. RISC basically stands for reduced instruction set computer. Okay. So, what do you mean by reduced instruction set computer? It essentially means that we have a reduced set of instructions, that there will be a limited set of instructions that will be used. And in a RISC machine, normally you will have loads and stores to access the memory. Other instructions will not directly access memory, and most of the other instructions will work on the registers. That is, you bring data from memory into the registers using the loads and stores and then work on those the values which are there in the registers. This is what happens in a typical RISC kind of an architecture. A CISC architecture, on the other hand, consists of complex instruction set computer. So, what is this complex instruction set? There is a single instruction may do many complex operations, right, or may do one big complex operation rather than doing simple operations only. And in this case, in a CISC architecture, typically what also happens is many instructions will work on both the register and the memory. That is, you may have a part of the instruction, that is a part of data which is required for the instruction coming from memory and another data which is coming from the register, and you have an instruction, an add instruction for instance, which will have part of the data coming from memory, part of the data coming from the register, and you will be doing an addition operation on this. You may also have 2 operands coming from 2 memory locations. All these combinations will be there in a complex instruction set computer. Okay, so that is, you will have a larger set of instructions which also do many more operations, whereas in a RISC machine you will have simple instructions which do limited operations. But the design normally is, the reason why we go for this kind of a simpler set of instructions is that the design can be simpler. So, you may be able to build a faster machine using a RISC architecture. Okay. So, generally, whenever we talk of instruction set, these 2 terms are very common terms, which is why I am introducing these 2 terms right at the beginning, that this RISC reduced instruction set computer and a CISC or a complex instruction set computer. So, to understand, we will use combinations of both, and then we will look at separating out the RISC features and the CISC features. Okay. Let us look at what an instruction format would look like. Instruction formats in general would vary, that is, different processors may have their own instruction formats, but in general you will find that an instruction would have these following features. Okay. That is, explicitly or implicitly there will definitely be an opcode which specifies what is the operation to be performed, and then what are the source operands. Obviously, you are doing some work on some data. So, what are the source operands? Maybe there are 2 operands, and then the destination operand, and then some control information which may be optional. But in general, any instruction would have place for all these different factors. Again, some of these may be specified implicitly, that is, it may be implied. Okay, it may not be specified explicitly in the instruction, it may be implied. That is a possibility. But in general, you know that these things should be there. Okay. So, if you look at an instruction format, for instance, so let us say I have an add instruction here. So, these first 4 bits may specify the opcode, and then the next set of bits may specify one source operand, next set of bits may specify another source operand. So, this is source 2, this would be source 1, and this would be the destination operand. There are some other control bits which are also provided here, but these may not be used. So, that is also a possibility. Okay. So, we have an unused set of bits here which may be used for some other instruction. So, which is why the instruction format in general is providing you all these features. So, just to give you an example of what an instruction would look like. Now, when we have these different instructions specified, we normally have certain notations that are used to understand how what these instructions do. Okay. One of the standard notations that we use is called as the register transfer notation. So, this register transfer notation basically looks like this. So, what it will do is you will have some mechanism by which you can identify a location by a symbolic name standing for its hardware binary address. So, for instance, you will specify something like location LOC, lock, okay, or R0. R0 would be the register name that you are using and so on. And so, the contents of a location are denoted by placing square brackets around the name of the location. So, you will have something like this. If I have for example, something specified like this R1 and an arrow which says that some data transfer or something is taking place from the right hand side to the left hand side, and then I specify lock over here. This means contents of this memory location specified by this lock are transferred to the register R1. Okay. So, here again I may have something like this. So, this says contents of R1 and the contents of R2. This is indicated by these two square brackets. So, I say contents of R1 is taken, contents of R2 is taken, the two are added together and that value is stored in register R3. Okay. So, this is one way in which you could specify the instruction that we have. Instruction format is the binary format in which that instruction would actually be used inside the computer. These notations are for us to understand what is happening. Okay. So, this is one notation that is used. Another notation that is used is the assembly language notation. Here again different processes may use their own different assembly language notations, but in general you can find a lot of commonality between them. So, here we represent these things in this manner. Okay. So, we have machine instructions which are represented like this. So, I would have something like move R1 comma lock. Okay. So, here you can see that this is a little more understandable than this kind of notation here, that is the register transfer notation that we looked at earlier, but this is the equivalent of that. So, what was specified here as R1 and then this left arrow and then this location within square brackets is specified like this now, move R1 comma lock. So, normally the convention that we use is that the destination operand is the one that is specified first and the source operands are specified later. Okay. So, right hand side is more like the source operand. So, move R1 comma lock here would be the contents of this location would be transferred to the register R1. Similarly, if I say add R3 comma R1 comma R2, this means that contents of R1, contents of R2 are added together and stored in the register R3. Okay. Equivalent of this register notation that we saw just earlier. Okay. As I said, different processes may have their own notation, but they are normally similar. So, we will use some general notations which are intuitively very clear to us. Okay. That is what we will use to understand various things. Okay. So, now this is to give you a sequence of instructions. See how a set of instructions is used to represent a particular to perform a particular operation. Okay. So, let us look at this now. So, let us say I want to evaluate this expression here A plus B into C plus D. Okay. So, I am assuming that I will use a RISC kind of an architecture, that is I will use loads and stores to perform all my memory operations and all the other operations will be performed with respect to the registers. So, look at this, I want A plus B into C plus D, right. So, what I will do is I will first have to load the value of A into the register, that is A is there in some memory location. So, that value has to be loaded into a register R1. So, I have an instruction like this, load R1 comma A. Okay. So, this is what happens in this instruction. So, next instruction would be load R2 comma B. Here what is happening is the contents in memory location B are added to register R2. Next instruction would be load R3 comma C. So, contents of memory location C are loaded into R3. Then I have a load R4 comma D. Contents of memory location D are stored into R4, and then now I start performing the arithmetic operations. So, I now have an instruction called add, which is now going to add R1 and R2 and place it in the register R1 itself. So, remember that this what you have to note here is the source operand and destination operand may be the same, but only thing is after this operation you have to remember that this contents of R1 will be overwritten by the sum of R1 plus R2. Okay. So, you can use this kind of a notation, but it will be overwritten, that is something we need to remember. If I do not have to worry about keeping that old value, I can always overwrite it. So, that is what we are showing over here, add R1 comma R1 comma R2, that is R1 plus R2 is stored into R1. So, now we have done this A plus B operation. Next what is to be done is we need to do the C plus D operation. So, let us say I do add R3 comma R3 comma R4. So, this is one example of the addition operation where we are using R3 plus R4 storing the value into R3. Okay, that is next. So, next I need to do the multiply operation. So, now I will do multiply R1 comma R3, right. I know that the two additions, the two sum values A plus B and C plus B are in registers R1 and R3. So, now I will multiply R1 and R3 and I am storing that value that result in R1 itself. So, R1 now has this function A plus B into C plus D evaluated. Now, what do I need to do next? Next thing I need to do is store this value into the memory, right. So, let us say I want to store it in a location x. So, I say store x comma R1, that is the value R1 is now stored into the memory location x. Okay. So, this gives you a simple sequence of instructions that one could use, okay, to perform certain operations. Okay. This is just a sample, you will become familiar with writing these kind of instructions. Okay. So, we will take a short break now and then come and look at different types of instructions. So, welcome back after the break. So, you are just looking at how a sequence of instructions can be constructed to perform a certain operation. So, now we will go ahead and look at how the organization of a CPU also influences the instruction format. Okay. So, now when we talk of organization of a CPU, of a processor, so there are different types of processors that one could design. Okay. The most common one that is used is what is called as a general purpose register based architecture. So, in a general purpose register based architecture, what we do is we use many registers, right, to hold all the operands, that is source and destination operands, in order to reduce the memory traffic. This is in fact the example that we just looked at now was based on some kind of a general purpose register architecture. So, and we saw how you could write a sequence of instructions for that. There are also other types of processor architectures which are possible. You could have what is called as a single accumulator based architecture. Okay. So, what is the difference here in this architecture is that we do not have many registers. Okay. We may have only a limited number of registers or no register at all, this is possible, but there is one special register called the accumulator. Okay. So, this accumulator will definitely hold one of the source operands. Okay. And so, the other operand may come from memory or may come from another register, okay, but the result is usually stored back in the accumulator. Okay. So, this is called as a single accumulator based architecture. So, therefore, what happens now, since your accumulators hold one of the source operands and the result always kind of goes back into the accumulator will have to be saved to memory quite often, okay, especially if there are no other registers, otherwise you will have to save it to some register. Okay. So, this is, and normally when we talk of a single accumulator based architecture, it means that there are no other registers and you only have one accumulator and the rest of it will come from memory. Okay. So, an example of this kind of an architecture is something like this. So, look at the single accumulator based architecture here. So, you can see what I have here. I have this ALU, which is the one that is going to perform my arithmetic and logic operations, right. Look at what is feeding into this ALU. I have an accumulator register which feeds data into this ALU and the output of the ALU is sent back into the accumulator. Okay. And then the other input to the ALU comes from this memory data register. Remember, our memory data register is our interface to the memory. So, from the memory, the one input comes to the ALU, another input comes only from this accumulator. So, now what happens, all the operations are performed over here. So, you have to perform an operation here and then store the value back into the memory. Okay. From the accumulator you will have to store it into memory and then again bring it back from memory and so on. Okay. So, you will find that the type of instructions we use in this case are a little different. So, which is why we said the organization will affect the type of the instruction sequences that we are able to construct. Okay. The third type of architecture that is that we talk about are stack based architectures. So, in stack based architectures, what we do is no registers and all operands and the result are always on the stack. So, everything is maintained on the stack. So, you will have an ALU, but all the data that is to be operated on is all on the stack. So, you have to bring data from the stack to the ALU, perform the operation here and store the result back into the stack. So, depending on what type of architecture we are actually using, you will find that different types of instructions are used and different types of instructions are designed. So, we will take a general look at that first. Okay. So, depending on this types of different architectures, you can see that the number of operands that need to be specified in an instruction will vary. Okay. So, we have, it may be 3 different addresses that need to be specified or 3 different operands that need to be specified. For instance, you may have to specify explicitly the source operand and the destination, the 2 source operands and the destination operand, or in one case, for instance, if you take the accumulator based case, since we know that the source and one destination is always one source and the destination is always the accumulator, you do not have to specify that explicitly, in which case you need to only specify one source, and one source is all that you may need to specify because the accumulator is already there. So, in which case I can reduce the number of operands that are there in the instruction. Okay. So, based on this kind of an understanding, we look at instructions as 3 address instructions, 2 address instructions, 1 address instruction, 0 address instruction, and so on. Okay. We will take a quick look at these types of instructions. Okay. So, now this is an example of a 3 address instruction. Okay. This is what we have looked at a little earlier. So, we say add R1, R2, R3. Okay. So, what is this? There are 3 different addresses specified. That is, what do I mean by address? That is where a particular operand is located. So, 2 source operands R2, R3 and 1 destination operand address R1. So, all these are specified explicitly in this 3 address instruction format. Okay. Next, if I look at a 2 address instruction format, I may have something like this: add R1, R2. So, what is being done here? Here the meaning of this is R1 plus R2 is stored in R1. Okay. So, this means R1 is serving as both a source register and a destination register. So, it is enough for me to just specify 2 values, but what is implied here is that this R1 will be both a source and a destination, that this R1 is also being used as a destination is implied over here. Okay. So, I need just specify these 2 values. So, this is called as a 2 address instruction. This may be used in certain instruction formats. Next is a 1 address instruction. So, what happens in a 1 address instruction is, okay, for instance, I have something like add M. This can be an example of a 1 address instruction. What is the meaning of this? This means that the other operands which are not specified here are actually there in an accumulator. Okay. So, I say, let us say AC is my accumulator. So, this means that the contents of memory location M, right, the memory address this memory location, the value that is there in this memory location is taken and added to the value that is already there in the accumulator and stored in the accumulator. Now, because this accumulator information is implied, okay, it is not specified over here explicitly, okay, because we know that whenever we do any add operation, it is always done on with respect to an accumulator. So, for instance, when we talked about the accumulator based architectures, the accumulator based architecture will normally have many such 1 address instructions that are used. So, you can see that the instruction will be smaller, right, because it only has lesser information that needs to be specified. So, that is an advantage of these kind of 1 address instructions, but we should know what is the implication here. In this case, for instance, we know that the accumulator will be one of the sources and also the destination operation. Okay. Another example is a 0 address instruction. As I said, 0 address instructions are normally used when we use a stack based architecture, because we do not specify where the data is stored. The data, by implicitly, it is there only in the stack, and where on the stack is it? Normally it is there in the top of the stack and 1 below the top of the stack, that is top of the stack and top of the stack minus 1. Okay. So, for instance, if you look at a 0 address instruction example here, I will just say add. So, what will this add instruction actually do? It will take a top of the stack instruction, I mean data in the top of the stack plus the data in top of the stack minus 1, add these 2 and place it back in top of stack. Okay. That is, if you remember your push and pop instructions that we talk about with respect to stack, basically what you will be doing is you will be popping the top of the stack, decrementing the point that will automatically decrement the stack pointer. So, you will take the next instruction that is there, next data that is there on the top of the stack minus 1, these 2 will be added, right, and that result will be again be pushed back onto the stack. Okay. So, this is what will happen in a 0 address instruction. So, this is example of a 0 address instruction. So, now we have seen that we have these different types of instructions: 3 address, 2 address, 1 address and 0 address. What we will now do is take a look at how the same evaluation that we did, right, of this formula A plus B into C plus D can be done in all these 3 methods: the 3 address instruction, the 2 address instruction and the 1 address instruction method. Okay. So, if you look at the 3 address instruction format for a plus b into c plus d. So, let us say for instance, I can write it as add r1 comma a comma b, that is I am assuming that memory location a, memory location b are all specified explicitly in this address, and that value will be stored in the sum of these two will be stored in a register r1. So, add r1 comma a comma b. What this will do for me is r1 in r1 memory of the value which is there in memory location a and memory location b will be added and stored. Okay. Add r2 comma c comma d, this is my second instruction, and this is my third instruction, which is multiply x comma r1 comma r2. In the 3 instruction format, this gives me a set of instructions that I need to evaluate this function a plus b into c plus d. You can see that just 3 instructions are required, one for doing one addition, one for doing the second addition, and the third one for doing the multiplication. So, this multiplication also stores the value, the result is also stored in the memory location. So, this is how 3 address instructions can be used. Okay. Now, the same thing now using a 2 address instruction. Okay. So, if I use a 2 address instruction, you would have something like this. So, I have for instance first move r1 comma a. So, which means I am moving the memory location a, contents of memory location a into r1. Then I am saying add r1 comma b. What does this mean? This means r1 plus the memory locations of b, this will be added and stored back in r1. Essentially what I have done is I have done a plus b here. Next I will similarly do move r2 comma c. I am now moving the value c into r2 and then adding r2 comma d, that is 2 with r2, which is actually the value of c plus d, this addition takes place, stored back in the register r2. Then now I have a plus b and c plus d in the registers r1 and r2. So, now I do a multiplication of r1 comma r2, this means r1 is multiplied with r2 stored back again in r1. Now, r1 has the final result, I stored that into the location x where I need to store the result. So, now I will do move x comma r1, which will store the value of r1 into the memory location x. So, you can see that this is what will happen in a 2 instruction format, and as you can see the number of instructions is slightly larger in this case. Next, let us look at the 1 address instruction. So, in a 1 address instruction, so again what is implied here, remember, is this is typically used in an accumulator based architecture. So, implication here is one source operand and one destination operand will be accumulator. Okay. So, here let us look at what we have. So, first I do a load a. So, what this will do is memory location a is loaded into the accumulator, we do not specify where I am loading into, right. So, that is automatically implied as accumulator. Then I say add b. What will the add b do? It will take the accumulator value, get the value from memory location b, add the 2, store it back in the accumulator. Okay. So, again remember lot of implicit information. Now, there is no other temporary value to hold this for me. So, I have to store it back somewhere. So, now I will do store t. So, store t means that I will store this value in this accumulator into a temporary register t. Now, similarly now I have to do the c plus d calculation. So, again I do a load c which will bring it to the accumulator, add d which will add the contents of this accumulator to d and store it in the accumulator again. Now, I do a mul t. This means this a whatever I have got, c plus d is already there in the accumulator, t has a plus d, a plus b. So, I bring that a plus b from the memory, multiply it with the accumulator value, store the value in the accumulator. So, now accumulator has got a plus b into c plus d. Now, I can store the value into the value that is there in the accumulator into a memory location x. So, I do store x, so which will do ac will get stored into memory location x. So, this is a 1 address instruction execution. Okay. So, now that we have looked at 1 address instruction, we will look at 0 address instructions later. So, let us first look at, there is one thing that we should have observed from whatever we saw right now, from the 3 address to 2 address to 1 address. What we observe is that using registers in general helps. So, we saw that when you use registers, you can number of instructions that we use are lesser. Okay. In addition to that, there are a few other advantages that we need to consider. So, they are the following. One is registers are faster. So, rather than bring it from memory, if I have to bring it from registers, that will definitely help. So, they are faster. And then my instructions on the whole, when I encode the instructions in the instruction format, I will get shorter instructions because I need fewer number of bits to specify the registers. So, for instance, if the number of registers is like say 32, then I only need 5 bits to specify a given register. Okay, that is the advantage of having specifying registers. Your instruction as such becomes smaller. And it is a potential speed up that you will get because registers are faster. And fourth point is it minimizes the frequency with which data is moved back and forth between the memory and the processor registers, because if I have more number of registers, Obviously, I can store the temporary values in the registers itself. We saw this in the single address instruction format, for instance. You have to every time move it back to the memory. We won't have to do it if you are doing it in the registers itself. Okay, so this is a general feel that we need to have, that we need to understand how these different register formats and things help. So this is again an example of the same A plus B into C plus D using a typical RISC based architecture. Remember, RISC based architecture, it's again a general purpose register. I will have lot of registers. Only thing I will make sure is all my memory access operations are all done only by using loads and stores. So if I use this kind of architecture, this is what my instruction sequence will look like. So I will do a load R1 comma A, which will load memory location A into R1, load R2 comma B, load memory location B into R2, load R3 comma C, load R4 comma C. So I have loaded all the values I want into R1, R2, R3 and R4. Now I have 3 instructions which do the addition and the multiplication. 2 addition instructions R1 comma R1 comma R2, multiply R1 plus R2 stored in R1, add R3 comma R3 comma R4, R3 plus R4 is done, stored in R3. Then I have multiply R1 comma R3, that is multiply R1 and R3, store it in R1, and then now I do a store operation, store x comma R1, which completes my instruction format. Okay. So to summarize, what we have looked at in today's lecture is we have looked at instruction types, instruction format, some notations for the instructions. We looked at 2 notations, the register transfer notation and the assembly language notation, and then we looked at different types of instructions in terms of the number of addresses that are there in the instruction. We looked at a 3 address instruction, 2 address instruction and 1 address instruction. We also looked at what is a 0 address instruction, but we need to look at some examples of that type. And then we also got the difference between what is a RISC architecture and a CISC architecture, or rather at least we know what is now meant by a reduced instruction set computer and a complex instruction set computer. A few questions now to revise the contents of today's lecture. Question number 1, what are the types of instructions normally used? Question number 2, give examples of control transfer instructions. Question number 3, give the register transfer notation for an instruction that adds 2 registers R1 and R2 and places the result in register R3. Question number 4, what is the characteristic of an accumulator based architecture? Question number 5, write a sequence of instructions to perform the operation A into B plus C in A, single accumulator architecture, B, RISC based general purpose register architecture. Thank you.